So here's a problem. 15 people are sitting around a table for a meeting, and it just so happens that everyone is sitting in front of the wrong name card. If we are not allowed to switch the cards or move the people, can we always rotate the table such that at least 2 people have the correct name cards in front of them at the same time? Today, let's talk about how solving this problem involves a simple concept that's not taught in the K-12 curriculum. My name is Dirdos. I'm on a mission to collect interesting math problems for school-aged children, and I'd like to take you along. My first guess on this problem was that it had something to do with 15 being an odd number or a multiple of 3. This was quickly debunked though when I started trying the smaller cases. With 2 people around the table, the name cards are either both wrong or both right. So if it's wrong in the beginning, turning the table around would make it right for both people. The situation is similar for 3 people around the table. If all name cards are in the wrong place, then we can match all 3 of them at the same time by rotating. There we do start seeing a case where one of them is matched correctly and the other 2 are switched, which was impossible for the 2 people case. If this happens, no matter how we rotate the table, only one person can match their name card at any time. The arrangements get a bit more varied in the 4 people case, but with a bit of patience, we can verify that anytime we have all the name cards in the wrong place, we can still rotate to match 2 or more name cards at the same time. Then, in the process of listing out the arrangements for the 5 people case, I noticed something. Here, if we turn the table, we see that B, D, and E all match their name cards at the same time, which means they were all the same number of spaces away from the right name cards before. That sounds like a pigeonhole problem. Here's the concept called the Pigeonhole Principle. Suppose you're a pigeon keeper, and your pigeons need to return to their pigeonholes to sleep at night. If you have more pigeons than pigeonholes, then at least one pigeonhole will have to accommodate 2 or more pigeons for the night. Notice it doesn't say anything about the other pigeonholes because it's possible that all pigeons decided to squish into one single pigeonhole for the night and leave the rest empty, or they could spread out nicely. But at the very least, you'll have one double-booked pigeonhole. There's also the generalized pigeonhole principle, which says if the number of pigeons that need to fit into the pigeonholes are more than n times the number of pigeonholes, then there's at least one pigeonhole that contains more than n pigeons. Again, notice that it doesn't say anything about the other pigeonholes because it's possible that we're just lucky enough to have all the pigeons bunched up in the same pigeonhole while the others are empty. But at least we have this one. In general, the pigeonhole principle can apply whenever we're sorting items into categories. In our round table meeting problem, for example, the people seated at the table are the items, and we can sort them into categories by how far, clockwise, their name cards are from where they're sitting before we started turning the table. In our 5 people case, a person can be 0 spaces from their name card, meaning they're sitting in front of the right name, or 1, 2, 3, or 4 spaces. We were told that no one starts out sitting in front of the right name, so there is no item in the 0 spaces category. This means we have 5 people sorted into 4 remaining categories. Therefore, at least one category contains 2 or more people, and these people will have their names rotated to the right place at the right time. Since the only requirement is that we have more items than categories, the same logic applies to any number of people around the table. As long as we start with everyone sitting in front of the wrong name card, there's guaranteed to be a rotation of the table that matches 2 or more names correctly. Phew, math makes sense again. There was a second part to this problem that asks for a way to arrange the people and the cards such that no matter how we turn the table, we always have one person matching the name, like the arrangement we saw with the 3 people case earlier. I wonder if that's a possible arrangement for any number of people around the table. Let me know what you think in the comments below. And until next time, stay curious.